This video is for Chapter 4, Section 5, and it's all about isosceles triangles. This is the final lesson for our Level 3 unit, in which we've been studying parallel lines, triangles, and polygons, and we're going to take a look at isosceles triangles. We're going slightly out of order here because I want to utilize the triangle sum theorem when looking at isosceles triangles. So, Chapter 4, Section 5, here we go. Isosceles triangles. First of all, we've defined an isosceles triangle as having two or more congruent sides. From here, we want to define the parts of an isosceles triangle. So, we have a vertex angle, we have the two legs, the base, and the base angles. It's important that we make note when you're writing down your notes, the legs are the congruent sides. We should always start there. The base then becomes the third side. The base angles are the ones that touch one of the legs and the base. One of the legs and the base. The vertex angle is where the two legs come together. That is the vertex angle. Second example over here. If you had to identify the parts of this triangle, it is very, very important to make in your notes that AB is not the base. Segment AB is a leg. The base is AC. This is very important. Base does not mean bottom. There's no gravity here. Okay. The two congruent sides are the legs. The base is the third side. The vertex angle is angle B. The base angles are A and C. Okay, now that we have the different parts of a triangle, we're going to go to the first theorem. Now, this theorem doesn't have a name, and what we're going to look at is the bisector of the vertex angle of a isosceles triangle. So, when I look at this, I want to make a drawing to show you where I start. First, just a triangle that is isosceles. Then I'm going to bisect the vertex angle. So the idea is if we have just these markings, we get the conclusion that it is the perpendicular bisector of the base. These markings right here are added in second. If I look at this picture, I notice that these two sides are the same, these two angles are the same, and this little side here in the middle, well, it's shared, so it's obviously congruent to itself. We should be able to see that these triangles are definitely exactly the same. This triangle is the same as this triangle. We can fold it on top of itself. So if these two angles have to be exactly the same, they both have to be 90. They have to be right angles. Therefore, perpendicular. It also has to split that base in half because it folds on itself. I like to call this the paper airplane theorem. We fold that isosceles triangle in half and everything lands perfectly on itself. So, if you have the perpendicular bisector, the bisector of the vertex angle, you get the perpendicular bisector of the base. Now, what we're going to do is look at what would we need in order to see all this. So, if we have a triangle, and we know that the triangle is isosceles, all we need is one of these other markings, and we get all of the rest. So, for example, if I have this, then I get these. I'll mark them with dotted lines. So, these two markings, you get all of that. If I was given this, given right angles, I can make the conclusion that these are congruent and these are congruent. So, no matter what, as long as I have an isosceles triangle, if I have an angle bisector, I get all of the things. If I have perpendicular to the base, I get everything. If I get the base being bisected, I get everything. All right? This is very important for the next theorem that we're going to move to. So that was just to take some notes about what this visually looks like. Now, the isosceles triangle theorem. This allows us to say that we can now prove that if two sides of the triangle are congruent, that I guarantee those two angles are congruent. Now, if you're taking notes from this, right now, it looks like everything is marked and we forget often what came first. So, we should make a little note that says, if two sides are congruent, then the angles opposite those sides are congruent. That is the isosceles triangle theorem. If two sides of a triangle are congruent, then the angles across from those sides are congruent. The best part about this is, there's a converse. Where did it go? There it is. The converse of the isosceles triangle theorem says if you start with two angles congruent, then it's a guarantee that the sides opposite those angles are congruent. This time I would draw my arrows pointing out to the sides, indicating angles first, sides second. Now, this becomes biconditional. If two sides are congruent, then two angles are congruent. If two angles are congruent, then two sides are congruent. So, two sides of a triangle are congruent if and only if the angles across from them are congruent. Two angles are congruent if and only if two sides across from them are congruent. Okay, now if I take all this, there's one other extension and then we do some examples. One extension is, this now means that if the triangle is equilateral, meaning all three sides are congruent, then it has to be equiangular. Because if all three sides are the same, then according to the isosceles triangle theorem, the angles across from congruent sides are congruent. So because these two sides are congruent, I would say these two angles are congruent. But because these two sides, I would say these two angles. Because of, let's see, these two sides, I would get these two angles. So realistically, if all three sides are congruent, then all three angles are congruent. And vice versa. So a triangle cannot be equilateral without also being equiangular. This is the one shape where those two things mean the exact same thing. All right, let's take a look at some sample problems. So here we have a triangle and we're being asked to solve for x and y. The most important thing to notice right away is this triangle is isosceles. And there's an angle bisector, which means, according to the very first theorem we learned, these angles must be right angles. So I've got y equals 90. Right from the start, y equals 90. Now, to find x, I'm actually going to say, well, I have this picture, I need to draw this here, and x is here, which also means x is here, because they're congruent. 63 is here, and according to the isosceles triangle theorem, if I erase this for a second, that means 63 is over there. And I have a 90 degree here and here. At this point, I only want to look at triangle number 1. And in triangle number 1, x plus 63 plus 90 will add up to 180. The angles of a triangle always add up to 180. So we put this together, x plus 153 equals 180, and x ends up equaling 27 degrees. That's example number 1. Now here's example number 2. The key in this example is to notice that there is a right triangle and an isosceles triangle. And there are a couple things that we want to address here. First, let's look at V. So in order to solve for V, I'm going to notice isosceles triangle. So V has to be the same as that angle there. Isosceles triangle has two congruent base angles. So now I can say, let's see, I've got 116 degrees plus 1V plus another V equals 180. That comes from this picture here. Congruent, congruent, 116, V and V. 2 V's plus 180 equals, or 2 V's plus 116 equals 180. I'm going to subtract the 116, and I end up with 2V is equal to 64. I divide that in half, and V is now equal to 32 degrees. I have solved for V. Now I need angle C. Angle C happens to come from a different triangle in which there is not isosceles. So I have a little bit of a problem here. I can't use the isosceles triangle theorem. I have to come up with something else. Here's my something else. Without drawing the other triangle, 116 is actually an exterior angle. I have two ways I can solve this now. I can say that 180 minus 116, which equals 64, produces this angle. Then I can use the 64 and the 90 plus the C to figure out what the angle C is. So I can take 180, subtract the 90, subtract the 64, and I end up with 26 degrees for C. There is a second method in which I will point out. Now you have to go back in the video if you want to write this one down. Another method is to take that 116 as an exterior angle and say that it is equal to the two remote interior. So then I can just subtract 90 and I get C is equal to 26. There are lots of different ways to approach problems using the triangle sum theorem. Keep in mind that every triangle adds up to 180 degrees, the angles, only the angles. And then we have all these other hints, like linear pairs that add up to 180, or isosceles triangles where two angles are exactly the same. We have to start using all of these little tricks and hints to figure out the measurement of the angles within a triangle or any shape for that matter. That is it. Those are answers from that example. That is it for Chapter 4, Section 5 on isosceles triangles.